something that's completely wrong, please do not interrupt him. Once he's done, we'll have time for questions. At the end of that time, we'll dismiss the general audience, and the committee will remain behind and ask some additional questions from Lieutenant Gordon. So those are the ground rules. Now, as far as Lieutenant Gordon, I just want to give a quick introduction. He developed a very good tool to locate and classify sunspots, which is the first step in my mind for utilizing it with the new satellite, the Space Dynamics Observatory, to try to see if we can come up with a better way of forecasting flares. So from his research, he's already generated 2 additional projects that will be continued by other students. So with that, Lieutenant Gordon, it's your time.
Oh, wow. Do I need to speak directly at that? Or...
Can you guys hear him?
I can speak
hear pretty good.
Okay. All right. So good morning, everyone. I wasn't expecting this many people, but that's good. I like talking in front of people. So again, like Dr. Acebal said, my name is Lieutenant Spahr, and today I'm going to be discussing my thesis research, which was on fully automated sunspot detection and classification using Solar Dynamics Observatory, Helioseismic, and magnetic imagery processed in MATLAB. Before we get too deep into it, I'd like to say thank you to my research sponsor, which was the Air Force Weather Agency, 2nd Weather Squadron. I'd like to note that this thesis was research priority number 11 of 13. And I'd also like to say thank you to my research committee, Dr. Acebal, Colonel Walli, and Dr. Bailey. So slide 3 here, overview of what we're going to be talking about. Next slide. So the best way to do this is to kind of start talking about what the Air Force does with sunspots. And so right now, we have Air Force solar analysts who hand classify sunspots once a day. And those reports that they create are sent to the Space Weather Prediction Center, which is basically the National Center for Space Weather. And then SWPC actually publishes the data for operational use. And the observatories that contribute to the SWPC report are all geographically separated. We have Learmonth in Australia, San Vito in Italy, and Holloman Air Force Base, which is in New Mexico. The way they classify these sunspots, we use what's called the McIntosh system for classification, and it's a standard that we use across all our observatories. And there are a total of 60 different categories in the McIntosh classification system that all depend on things like sunspot length, or group length, and sunspot polarity. And the reason that we're interested in this is because certain McIntosh classifications are actually correlated with solar flares. So that's the big why do we care. Slide 5. What's the goal of the research? Well, so sunspots can actually be more dynamic than the single day sample that we get from the SWPC reports. And so the question we want to ask then is, what if we can do this process faster? Because the drawings can tend to take some time. What if we had a sun-focused satellite that could produce images at a very fast cadence and a high resolution? And the question there is, well, can we create automation that can give us faster or more consistent results? And then the big part here is, well, can we actually remove observer bias too when we do this automation? So those are the questions we want to ask. All right, moving into background, slide 7 here. Quick overview of the sun. So the image there on the right, I have pictured what is typically referred to as a quiet sun. This picture is taken from solar minimum. And the quiet sun is basically that's a term used to refer to any region that does not have any active regions associated with it. And the picture, I like this picture because it illustrates one of the key things that I needed to take into account when actually starting this research, and that's the concept of limb darkening. And we can see at the center of the sun in this picture, it's a little more yellow, it's a lot brighter, and then as you move towards the limb, it becomes more redder or darker. So that's something that we need to take into consideration because we're dealing with sunspots in the photosphere here. Next slide. now this picture is for solar maximum. We can see a large number of sunspot groups on the sun, and so I want to define quickly. Sunspots are just optically thick regions, and they appear darker than the quiet sun. They're mainly comprised of two basic regions, and there's an umbra, which is the center dark region of the sunspot, and the penumbra, which is the not so dark region surrounding the umbra, but it's still dark compared to the rest of the quiet sun. I'd also like to clarify that there's a difference between a sunspot and a sunspot group, the latter being just a combination of sunspots that are that meet a requirement for proximity to other sunspots and the proper polarity requirements too. And we'll talk about that in a little bit. And then on slide 9, just the I want to highlight that the solar cycle is something that I also needed to consider. Every 11 years or so, the sun reverses its magnetic polarity, and we kind of track the solar cycle using the sunspot number, and there's clearly a maximum and minimum point with a period of, like I said, about 11 years. So slide 10 here, I want to highlight the differences in the McIntosh classification. So I talked a little bit about the fact that we use the McIntosh classification system at all of our solar observatories, but the McIntosh system is divided up into 3 different parts. And so we have their number 1, modified Zurich classification, 2, the penumbra classification, and then the third part is the compactness classification. So each one of these has a letter, quote unquote, that is associated with that part of the classification, and the McIntosh classification requires that you have a letter from each of the 3 different parts. So the first part here, the modified Zurich classification, we have A through F and then H, and as you can see, most of those spots generally most of those classifications deal with the sunspot group length or the fullness of the penumbra. The second one is the penumbra classification, which has to do with the size and the shape of the penumbra surrounding the largest sunspot in the group. And then the last one there, the compactness classification, simply has to do with the spread of the sunspots between the leading spot and the trailing spot. I want to note that not all, so there's 7, 6, and 4 different different parts of those 3 different classifications. Not all combinations are possible. For example, if you have an A Zurich classification, that's a unipolar spot group, and so you're never going to have a trailing spot for that particular classification, and so therefore the only possible compactness classification for an A is an X, because you can't have there's no other polarity there. Okay, so on slide 14, I want to highlight some inherent disadvantages with the hand drawing method used at our observatories. So there's poor measurement precision associated with the drawing process. We're using an 18-centimeter drawing board, and so it's a pretty small projection of the sun. A lot of times the quality of the drawing can depend on the visibility for that day. The Air Force instructions associated with actually going and classifying these sunspot groups can sometimes be ambiguous, and so the interpretation of those guidelines can often depend on the analyst's experience, things like that. And frankly, the process can take a while, so there can be lag between classification steps that can introduce error to the process. So we want to, so that's a disadvantage there. And then the last bullet I separated because I want to highlight that. There are solar analysts that sometimes have more pressing issues to take care of. You know, the purpose of this is to track flares. So if there are flares going on, the analysts aren't going to be able to complete the drawing in a timely manner, and oftentimes you could be waiting to complete the drawing for up to 2 to 4 hours or something if there's a lot of flaring events going on. So and those flare events take precedence over doing the drawing. Next slide. So the thing that I wanted to use here is the satellite, the Solar Dynamics Observatory satellite. And specifically I'm going to be using, I used the images from the Helioseismic and Magnetic Imager, the HMI instrument. And this instrument produces very high resolution images that are approximately equivalent to about 95 micron pencil accuracy on a drawing board. So we have really good accuracy with these images. And the HMI produces spatially and temporally synchronized images that come out at a really high cadence. So this is exactly what we're looking for our automated process. And this gives us practically continuous observation of the sun from its inclined geosynchronous orbit. So this is exactly what we need. All right, so on to slide 17 here. The code that I developed can be broken up into 5 basic parts. The first part here deals with the acquisition of data from the satellite. We get that directly from the NASA website. The second, so I should mention that there's an intensitygram image and a magnetogram image that we take off that directly from the satellite. The second part here, we do some data manipulation where it's basically some image processing steps that give us what we want. A thresholding step where we detect all of the sunspots that are visible on the sun. Once we've detected all the sunspots, I want to go ahead and group all the sunspots in the appropriate groups. And then the last step there is simply the end product, the classification of the groups that I detected. So on slide 23, the HMI produces an intensitygram image, so the HMII, and this image has about 4 times, or at least 4 times more resolution than previous satellites used, for example, the SOHO satellite. And there's some pre-processing associated with those images, but those are mostly limited to things like correcting for hot pixels on the CCD, and then any rotation correction that has to be applied based on where we are in our orbit. So after that, next slide, the first thing I want to do is an edge detection. And to do this edge detection, I use what's called the Canny edge detector, and it's kind of similar to, essentially it uses a Gaussian smooth, or it uses Gaussian smoothing, and then it calculates a local gradient at each of the at each point on the image, and this gradient is just a derivative approximation essentially. And if the gradient is high enough, then if it meets a certain threshold, then we say, oh, hey, that's an edge. That's part of an edge that we've detected, and it's that pixel that qualified for the edge is turned on. So it'll be a white pixel, and anything that doesn't qualify is going to be black. Then we suppress all of the points that aren't maximal rate of change or maximal change in pixel intensity to get a good, nice, really clean edge. And then we connect all the edges to make sure we have a good circle. After the edge detection step on the next slide, I want to go ahead and detect or figure out what the center and the radius of the sun is. And so to do that, I use what's called a circular Hough transform. And the way I like to think of this is we have all of our edge points that we had in the previous image, and we transform those into parameter space, which is essentially instead of x, y, and z, you basically have axes that are analogous to the parameters that you're trying to find out. And each of the points that you transform into this new space vote on the best representation for that particular, for the best representation of the circle that makes up the edge. And then after you have the best fit circle, you transform that back into real space, and you can end up with sub-pixel accuracy for what your center and the radius of the circle that you just found is. So very good method. After I have the center and the radius, I want to then go ahead and correct for the limb darkening that I talked about earlier. So the equation that I've written up here on slide 26, I have a ratio of intensities. The upper one has this function mu in it, which is mu is defined as the cosine of the theta, or theta, which is the angle off of the center. So think of the intensity at some angle off of the center of the sun, and that ratio or the ratio of that to the intensity in the very center of the sun. so that's what that equation is showing. And we get some, there's some relationship as a function of mu. And so I know now, because I have the center and the radius location, I can figure out what mu is, and then I can subsequently correct all of the pixels using this limb darkening correction process. And then pixels that are outside of the sun are set to basically the average intensity, so that we bring every pixel up to kind of the same level. All right, so on to slide 27. I take the corrected image that I had, and I simply add that to the, or I take the limb darkening corrected image, and I add that to the gray image, and I end up with something that gives us a pretty nice flat sun. And then the next step is I invert that so that all of the pixels that are associated with the sunspot regions have high intensity or high pixel count values. You can see them there in white on slide 28. And one thing to note here is that you can kind of see the correction is valid past approximately plus or minus 75 degrees. So that's something to keep in mind when we actually go to analyze the results here. So after I have corrected for the limb darkening, the next step that I want to do is find all of the sunspots in the image. And so I like to use, or I use this process that I like to call an iterative thresholding technique. And in the very center of this image, I have the sun that was from the previous slide, and I've taken a slice out of the rows, and I've plotted those at the very bottom of the slide with a pixel count. And you can see there, every once in a while, you get these spikes that go up, and those are the sunspots that we're seeing. So I want to go ahead and find those. So what I do is I lower the threshold step from 1 to 3 at the top here. And as we lower the threshold, green, yellow, red, the sunspots, the pixels associated with the sunspots start to get turned on. So anything that is above the line, any pixel that has an intensity level above the line is flagged as part of the sunspot group, and anything that has an intensity below it is not part of the sunspot. So after we after we start detecting a lot of spots, then that means we're into a noise level, and so we stop the threshold at that point. And so what we can see from 1 to 3 there is we basically are growing the sunspot regions into the appropriate region without altering any of the data. And then the final result, we actually smooth that to eliminate any of the noise associated with it. So next on slide 32, after I have all the locations for the sunspots in black and white, I want to go ahead and I can find which pixels are associated with those sunspots, but I need to have those locations in comparable units. So I want to transform everything into longitude and latitude values, because that's what is reported generally from SWPC and our observatories. So essentially what I do is I have the radius and the pixel, or the radius and the center values in pixels, and I get the B angle, which is essentially the tilt towards or away from the observer, and I can use some spherical trigonometry to figure out what the longitude and latitude of each of the sunspots is. So after I have the longitude and latitude on slide 33, I want to go ahead and group all of the sunspots that I detected. And so to do that, the groupings actually depend on sunspot polarity and the separation distance from other sunspots. And I mentioned the magnetogram image earlier, so that's when this comes in. And I've highlighted the different regions of magnetic polarity on the image on the right there. So all the sunspots that are red are associated, or they have the same magnetic polarity. They have a southern magnetic polarity, where the blue ones have a northern magnetic polarity. And the grouping then is performed based on the process that is used at Holloman Air Force Base for the same hand drawing method. So same process. And then after the grouping, so we detect, after we've detected the spots, we test those spots that we found against candidate groupings, and if the distance and polarity requirements is satisfied, then we say, hey, that's good, it's part of the group, and we renumber the sunspot with the appropriate group number. So on slide 35 here, after we have the groupings, I want to go ahead and classify those sunspot groups. So the first step then there is to, I basically have 3 different categories of the McIntosh classification. So 3 different functions for the 3 different letters. And each classification step is then performed based on the McIntosh standard, which is the same as the Air Force observatories. On slide 36, it's basically a representation of the logical process that goes behind each of the determinations of the classification. So at the top we're basically asking a question: is this threat or is this requirement met? If yes, then one way; if no, and this basically propagates down until you have an answer for which classification is appropriate. And so we calculate all of the required information for the functions to work, and then we use this logical process to figure out what the appropriate classification would be. And this one, for example, is part of the modified Zurich classification. There are other trees that would look similar for the other parts of the classification. The important factors that we want to catch here on slide 37, I mentioned that we want to calculate these specific items. So the things that we're paying attention to is the length of the sunspot group, the polarity of the sunspot group, area, eccentricity of the largest spot, length of the largest penumbra, completeness of the penumbra, and then the spread of the sunspots in the group. Okay, so after all of this is done, on slide 38, we have a result, which is this automated classification tool. And so really good, awesome. And so now that I have this tool, well, what do I want to do with it? I want to compare it to some things that, some standards. So what is the standard? Well, SWPC, the Space Weather Prediction Center, is the official U.S. standard. They put out the reports. And we have Holloman Air Force Base, which is a trusted source of data. And so what I can do then is I can compare the two. So we're not really sure which one is correct. SWPC has results and Holloman has results, but we're going to compare those results together, find out what the difference is, and then I can compare my results to both SWPC and Holloman and see if the difference is comparable. And so this sets up kind of a baseline, and after we set up the baseline, well then we can make comparisons to the output that my code created. So what do I want to evaluate with this? I want to look at the number of detected sunspots per day, the number of the total sunspot area, number of groups, the position of each of the sunspot groups that I found, and then the classification for each of those matched groups. And the reason we do this is just to make sure that, hey, I don't want results that are out in left field. I want to make sure that what I have is appropriate and makes sense with what other people are saying. So in order to do this verification, I collected data here on slide 40. Data spanned an entire year, and the images that I selected were closest to the Holloman reporting times, as close as I could get. And the first 6 months of data that I used were basically to develop the algorithm and test it. And then the second 6 months, I used this kind of a blind test to show that the results I got were consistent across data sets, because it doesn't really matter if you have a code that can do one data set perfectly if it doesn't work on real data. So that's what the second 6 months was for. So moving into some results. On slide 42, I want to mention some caveats that go into the comparisons. The SDO groups that I detected were actually confined to be greater than, for areas greater than 0.3, and the units there are millionths of a solar hemisphere, which is the typical unit that area is reported in. And this is approximately 2 to 7 pixels, depending on where you are on the sun. The reason I cut those out is because we're simply not going to get spot groups that are that small, and those could be considered pores in some cases. So we want to cut those out. The SWPC and Holloman groups with longitudes that were beyond the 75-degree cutoff that I talked about earlier were excluded from the test set. And then days where we didn't have data from one of the sources, I also cut those days out from everything, so that we had consistency. And then the SWPC reports actually come out about 8 hours after the Holloman reports. And so to correct for the position error, I simply shifted those back by about 4 degrees and, in order to sync up the reporting times. So now that we have our method established, on the next slide, I want to compare I want to first start out by comparing the number of spots that I've detected. So the plot here shows a difference between the number of spots that were reported by SWPC and Holloman. So I've subtracted the number of spots from SWPC and Holloman, and you can see that most of the results are pretty much around 0. The difference is around 0, which is kind of what we'd expect. There's some spikes, but most of it is around 0. Then what I want to do is I add the SWPC minus SDO. And what you can see here is pretty significant separation between the number of spots between SWPC reports and the SDO code. And the reason for that, I expected this because, well, first of all, we have better spatial resolution, so the number of spots that is detected by the code should probably be greater than the number of spots that are detected by, or that are reported by SWPC. And then, of course, the Holloman results are pretty much going to match that. And we expect them to be negative because we're taking a big number and subtracting that from a smaller number. So now I want to move into some regression plots. And so on 46 here, what I've plotted is the total number of sunspots. And we have SWPC to Holloman, SWPC on the y-axis, Holloman on the x-axis. And you can see there's a slope associated with that of about 0.94. So we can conclude from this is that the Holloman number of spots that are reported are slightly bigger than the number of spots that are reported by SWPC. And then when we do SDO to SWPC, we see a pretty significant tilt in the number of spots, which is again what we expected. We're detecting more spots, so we should have a tilt. And the slope there, about 0.46, tilted towards the SDO axis. And then again, consistent results with SDO to Holloman, the same kind of tilt that we saw before. So all consistent results there. Next thing on slide 49, I want to talk about verification of area. So again, I've plotted SWPC to Holloman, or SWPC minus Holloman, and you can see the variation is roughly around 0. There's some slight peaks, but nothing out of the ordinary there. And then what I want to do is add the SWPC minus SDO. And what you can see is the total difference in the area is approximately equal, more or less, to the SWPC minus Holloman region. And so that's good. That's a good result. And then, of course, we add Holloman minus SDO, and the results are pretty standard. And we have some slight spikes, but for the most part, we're roughly around 0, which is what we'd expect. So now moving into some regression plots for the area, we have the total area for SWPC and then the Holloman total area, and the slope here is tilted slightly towards the Holloman axis, indicating that Holloman may actually report areas that are greater than the SWPC reports. We have SWPC to SDO, and we can see that the results there are kind of what we expected, a slope of 0.94 towards the SDO area. So pretty consistent with the previous slide. And then the SDO to Holloman was also pretty consistent, so I just left that out. Next thing I want to do is compare the number of groups that the SDO code calculated versus the Holloman and SWPC reports. So here I have SWPC minus Holloman, pretty much around 0 with some slight oscillations. The numbers are smaller because, of course, you don't have that many groups. So SWPC minus SDO, in the next slide, there we can see some slight variation. We're mostly around 0. There's some that dip down to smaller or a larger difference in groups. And then definitely we see that trend with the Holloman minus SDO too. And so part of the reason for this is that if we're detecting more sunspots, then it's probably reasonable to assume that we're going to detect more sunspot groups too. That's just a consequence of having the better spatial resolution, and so accounting for more groups makes sense. And we see this too with the regression plots, smaller intervals. So in slide 57, we have the SWPC to Holloman, and the regression is about the slope of the line is about 0.81, and so slightly tilted towards the Holloman number of groups, and then the regression again tilted towards SDO, the SDO axis, and the SWPC to SDO, which is what we'd expect from the difference plots. And the same can be said of the SDO to Holloman, but I just so. All right, so on slide 59 here, after I've kind of established that all of the parameters that I'm calculating are consistent, I want to compare the classification. But before I can do that, I need to match the sunspot groups that I found versus all of the other groups that were detected. So, so in order to match, I use a position matching, and so anything I compare to the most appropriate group that is within 10 degrees of the candidate that I'm attempting to match. And so after a group is matched, well, then we take that matched group off of the, we take it out so that we don't double count it, basically. I want to mention before we get into the position results that there was some errors in the data that was actually put out, and so Holloman puts out their sunspot drawings, and when there was a significant deviation in one of the results that I found, I could go back and look at the drawings, and there are actually errors associated with the position and the classification in some of the Holloman reports. For example, the drawing would say it's at longitude of 55 degrees, and then the report would say 65 degrees. And so they might seem kind of spread out, but approximately 3% of all of the data that I found had some error in the report for that day. So that's something to consider. I couldn't do this process with the Space Weather Prediction Center because they don't produce drawings. But I think it's important to mention that there were errors in the data set too, so there could potentially be other errors. All right, so now moving into the position matching. In this table here on page 61, we have Holloman, SWPC, and SDO in the left-hand column, and you can compare Holloman, SWPC, and SDO to the same three across the top, and you can't compare to yourself, so the center or the diagonal there is not applicable. And so the way that I read this is that of the 707 groups that Holloman detected, the Space Weather Prediction Center missed 8.6% of the groups. And when I say missed, I mean they didn't, or they had a group that wasn't matched, essentially. So the Holloman proposed a group, and the Space Weather Prediction Center didn't have a group to match that particular group. So they missed 8.6% of the groups, whereas the SDO only missed 3.8% of the groups. The trend continues for the SWPC comparison, and what we can see is that the SDO code misses the fewest number of spots compared to the Holloman and SWPC reports. One thing I'll note, though, is that on the next slide, you see 26 and 25% there. Holloman to SWPC miss percentages of the SDO code is pretty significant. And that's what we would expect. If I'm detecting, more spot groups, 25% more spot groups, then yeah, we're not going to have those, the Holloman and SWPC reports aren't going to be able to match those groups because they didn't report them. So it's important to note too that the majority of the missed groups are often small, but what we can conclude from these results is that the accuracy for the detection of the groups is good. So we want to move on then to the actual classification comparison. So on slide 63 here, the next step then is to compare the classifications of the groups that were matched. And to do this, so we like I said, there are 60 different classifications. So I tally this in a matrix, and the matrix is 60 by 60 for the different classifications. And so in order to evaluate the accuracy of the classification, I defined 3 different metrics on slide 64. The first metric here is the direct metric, which everything then is on a diagonal of the matrix, where all 3 of the different letters of the McIntosh classification match. The intermediate metric, the next one, matches all the modified Zurich classifications, which is still kind of on a diagonal, and then the relaxed metric accepts classifications that are slightly off the diagonal, but in neighboring Zurich classifications, and those are accepted under the relaxed metric. Here's a depiction on slide 65 of the metric that I'm talking about. I tried to color code the different metrics and the combinations there. So on the diagonal of the matrix, we have the direct metric. So if you get everything right, then you're on the diagonal. And then you have slight deviations off to the side. And the order, I've listed the order across the top there, and then the Zurich. So for example, the order of the Zurich classification, AH, B, C, D, E, F. Okay, so on slide 66, now we're going to go ahead and compare the matches that we have. So the first thing I want to highlight here is the direct match. And you can see that the direct matches are low across the board. For the SWPC and Holloman matches, only about 33% of the time, 1 out of 3 times, do all of the different parameters in the classification actually match. And the same is true of the SWPC to SDO. And we have some pretty low match percentages there. I want to highlight too, I have a trained data set at the top there, and then the evaluated data set at the bottom in green. So we see the 2 different sets of data that I looked at. In the next slide, I'm highlighting that actually the intermediate and relaxed metrics contain more similar results across each comparison, as we would expect. Once we get to the relaxed metric, actually we're within 10% match for all 3 comparisons, and so that's good. There's pretty consistent results too compared to SWPC. And then on slide 68 here, I'm highlighting that we have consistency across data sets too. So there's a consistency between the trained data set and the evaluated data set. And we have pretty consistent results between those 2. So promising results there. So on slide 69, I want to highlight that the classifications that were produced by SWPC and Holloman are pretty much expected to have good results. So there's some data exchange that goes on between SWPC and Holloman, and they're always talking back and forth, and the Air Force observatories talk back and forth to other observatories too. Just to confirm what they're seeing. And so it can be said that the Holloman reports influence the SWPC reports, and the same is true, the reverse is true of SWPC to the Holloman drawings. Sometimes they can influence the groupings. And so what I want to emphasize with what I've produced here is that I've obtained approximate classification to both the SWPC and the Holloman reports with no outside influence whatsoever. I'm simply using the data from the SDO and getting these results. So that's really awesome. So what are some of the applications for the code? Well, I looked into that a little bit. We can actually improve the match percentages that were achieved. And so to determine those improvements, I'm on slide 70, a new metric is actually developed, and so to track these improvements, I used what's called the weighted bias sample variance, and so that's the parameter sigma there. And essentially, what we're doing is we're weighting the distance off of center that each of the classifications achieve in the matrix. And so we take the diagonal, or excuse me, I take the row and the column for each different report, and then I weight that, and W in this equation is the number of counts, and X is essentially the matrix element that corresponds to that particular classification. And so when we calculate this parameter, the name of the game then becomes alter the parameters, alter the parameters that go into calculating the McIntosh classification system in order to minimize the value of this weighted bias sample variance. So the theory behind this is, well, we have 3 different reporters that are all, in theory, using the same data. each reporter then is going to go off the same standard, which is the McIntosh standard for reporting the data. And so if we have a consistently biased observer, which is the SDO code, a code that does it the same way every time, and we alter the cutoff values associated with the specific McIntosh parameters, and we actually improve the match percentages, then the new cutoff values that we are using may actually be more appropriate. They may be more representative of the practice method that is used at Holloman. So we apply this concept to the Holloman data set, and I looked at 3 different categories here. The sunspot group length, the sunspot length, or the largest spot length, and the sunspot eccentricity. And what I've showed here is that as the variance decreases, then that change is positive. And what we can conclude then in the table there is that, so we have biased values and nominal parameter values, and there's a difference associated with each of the 3 different parameters that we calculated. For the sunspot group length, there's a difference of 2.5 degrees, which is pretty significant. The sunspot length bias is greater than 1.4 degrees, and then the sunspot eccentricity was found to be biased at 0.3, or the difference is 0.3. And so the result here is that I've essentially used the code that I developed to evaluate the Holloman classification bias, or the bias imposed by the observer in general at Holloman Air Force Base. Okay, so on to slide 75. I want to highlight some of the results here. So what I've done is I've produced a fully automated sunspot detection and classification code. I evaluated the accuracy of my code, and I showed that I get consistent results near the difference between the Air Force Observatory, Holloman Air Force Base, and the national standard, which is the Space Weather Prediction Center. And then I've determined the bias associated with the Holloman classification method for 3 separate McIntosh parameters. So for some future work on slide 76, some additional things that I'd like to do would be to explore other options for detecting sunspots, for grouping faster, and then having a more accurate code in general. I'd also like to create additional metrics to evaluate the accuracy of my code. I'd like to further study the Holloman Air Force Base observer bias. I'd like to evaluate or expand the bias evaluation to other Air Force observatories. Remember, we have 2 other observatories that we can evaluate. And then another cool thing that we could do would be to generalize the code to work on a bunch of different data sets. So not only can we use the SDO code, or the SDO images, we could use SOHO images also, which would be really neat. So with that, I would like to say thank you for everyone. So thank you to everyone for coming, and I will be happy to take your questions.